We are going to use cross-val score with some alternative regression scoring metrics, in particular the negative root mean squared error. So what I would like you to do is to potentially use your Convert Regression to Classification Colab notebook created earlier, and I want to load a new notebook with the bike rentals data set. Okay, so I have my notebook up from before. I went into my Google Drive to find that, and I'm not going to bother df.head since it's already been verified. I'm just going to get the data in there. You can do this on your own. Go ahead and even use X and Y. Okay, in this case, we're just using the regular C and T because it's regression. We're not trying to create any new columns. Okay, so open up a new Colab notebook. And let's call this one, let's call it maybe regression metrics in cross-val score. Okay, and we got to put the bike rentals data set in there. And then I'm just gonna go ahead and divide it up into X and Y. This one's already ready to go, so I can say X equals df.iloc, all rows, which means colon, and then all rows leading up to the last row. I mean all columns, and then Y equals df.iloc, similarly all rows, which is colon, and just the last column, which is a -1. Okay, and yeah, I do like, I say you don't need the df.head. I do like doing a quick check. When I check X head for a change, does X look right? It's a data frame, so, it does. It's missing the last column. Everything else, I'm going to assume everything's good to go. If you want to be thorough, of course, you could check Y head too. But okay, so how are we going to do this? I'm just going to call this load data, prepare X and Y. Well, cross-val score makes it relatively straightforward. Okay, let's just import some regressors from well, first let's get in cross-val score. So from sklearn.model selection, import cross-val score. And now let's try from sklearn. Let's use I'll do a few. Linear model, import linear regression, and then from sklearn.tree, import all the ones that you know, okay? Import decision tree, it's regression, so we've got to use the regressor. From sklearn.ensemble, import random forest regressor. From XGBoost, import XGB regressor, and comma XGB RF regressor. And you may wonder, is there a k-nearest neighbors regressor? There is. So from sklearn.kneighbors, .neighbors, sorry, import k in k-neighbors regressor. Okay, quite a few, but it's just fun to see how they compare. That's how you start to learn which regressors are better than others, and there are plenty more. Okay. By the way, just to follow up, some of you may wonder more about but how do these decision trees, random forest, and XGBoost work? And I'll try to provide a little more insight in another lesson on that. So what do we do? Well, we've used cross-val score. Let's go ahead and use it. Let's just, you know what? Now that we know we're doing a little bit, let's just go ahead and use the function. So def, I'm going to call it cross-val. The input's going to be the model. And then you should see for yourself, can you actually deliver both the cross-val score, the folds, and the mean? So try it. Score is equal. Let's reuse cross-val score. We need the model, x comma y. Okay, and we haven't checked the cross-validation yet here. We'll come back to that in a minute. So I want to print the scores. Then I want to say the mean is equal to, oh, what the heck, I'll just do print scores.mean, right? Same thing. Last time we said mean equals scores.mean, print mean. Okay, so that seems good. The only addition I want to make here is the last time we changed the default CV. Well, you can turn it into a name parameter here. Like the default is 5. You know, should we use 10? Last time we used 10. Why don't we use 10 and then we can switch it to 5? Now, if I'm going to change it there, you've got to change it here. So CV equals, and do you know what that should be? It's actually CV. Because how does CV assigned here in cross-val score? Well, we want to assign it the value that we put up here. Then we could use a different number, you know, different like variable. You could say, well, it's the folds. There are 10 folds. I'm going to set CV equal to number of folds. Okay, that's fine. Personally, I like to say CV because I like it the same in the different places, even though it looks a little weird at first because you see CV equals CV. So you can do what works for you. Right, because again, last time, when you read this, okay, you're assigning something to CV. What is it? What's the variable CV? Well, where has that variable been defined? It's going to look for it. It's been defined up here. That's 10 by default. So we can change it to 5 depending on what we get. We'll probably just leave it. Okay, so run that. Now let's try it with our list to start with. Okay, we're going to make a modification, right? Because this is on, what are we doing, metrics here? Yes. So what's the default? What's going to happen? Well, let's try linear regression. Okay, something is off. It says missing X. Oh, because do you see why? Cross-val score. This is the issue when you're doing like naming them similar. I want cross-val, right? Because cross-val score does need X. Look at that. It's doing the R2 score and giving you negatives. Okay, this is a problem. Like it's you're like, is it really that bad? I don't know. It's not the best metric. We're going to change the metric, okay? So here you go. Okay, we're going to have to make some modifications. Scoring equals, and then put in negative mean squared error. Okay? So, what that's going to deliver are the negative mean squared error. In fact, instead of calling the scores, I'm going to put this on a new line. I'm going to call it negative mean scores to be clear as to what it is. Okay, why do we change it? Because it's not the negative means. Negative means squared. Okay, it's the negative means squared scores. It's not the right units. Okay, but it's the Euclidean metric. It's what you do when you're computing distance. It's the Pythagorean theorem. A squared plus b squared equals c squared. Everything's squared. So you got to square root it. So to get the scores, you square root that. Okay, and you make it negative because you're going to turn it positive now. So you want the negative of the negative mean squared scores, okay? By the way, that is a list, or is it a NumPy array? It's a NumPy array, so we can just do this. It's going to do it for each individual piece, okay? And then you want to take it to the 1/2 power, right, which is 0.5. So do that now, okay? This is the best way to look at the regression scoring metric. Again, what are we doing here? We're changing the scoring metric, okay, standard, to negative mean squared error. But that's not the right unit, so we make it positive by taking the negative and taking it all to the 1/2 power. Now it's the correct units. Now if we got 21, which we won't, but it would be, oh, on average, we're 21 rentals off of the expectation, okay? So after your updates, run the function again. Run with, say, linear regression again. You can pick another model. It doesn't really matter. And you get a bunch of numbers, and you're like, okay, how do I make sense of the numbers? Well, you need to know, this is the one issue with the root mean squared error. You have to be able to interpret that. 972. That's not good or bad by itself. It depends on the range of the output, right? Because if the output here is like, if the ranges are like, they're in the 10,000s, millions, 972 is close to zero. But if it's like hundreds, that's pretty bad. So we've got to look at the stats for Y. Okay, that's the column that we're trying to predict. These are the count. These are the rentals. We've done this before. So if you remember, the mean is about 5,000. And very importantly, the standard deviation is 2,000. That means you can expect, on average, that the data is going to be 2,000 off from the mean. So if your root mean squared error is less than one standard deviation, here it is by about half, it's actually not bad. Okay? You're doing better than one standard deviation. Let's see how the other models do. Let's call them out. What do we got? We've got a decision tree. Worse. I'm just looking at the mean here. We've got a random forest. Taking some time here, right? It's amazing how fast they're. A little better, right? Because, it's doing 10 folds. Look at this, you guys. What's the shape of this data set? Oh, it's not that big, 731 rows. But still, you're doing like 10 folds, so that's 7,000. Okay, look, it's 731, 7 times 10. 700 times 10, there's 7,000 entries, okay, about. But when you do 10, that's 70,000. But the random forest is like 100 trees, so it's 7 million entries here, and it gets it really quickly. Try with XGBoost. Warnings, I'll show you how to fix those later. 797, remember lower is better, so this is definitely the best. And try the RF regressor. Get the same errors, not quite as good. And finally, let us try our new friend, the K-neighbors regressor. Remember how you can change how many neighbors it is? Not good. Let's change it again. Remember before, was it K? I don't remember if it's K. So maybe, if last time I got good results, 20. Okay, it's not K. Is it N for neighbors? It could be even N underscore neighbors. There it is, N underscore neighbors. No double equals. That would be equivalent to it. Won't work. Yeah, that's fair. 10. Yeah, this might not be the best one for K nearest neighbors. Sometimes it's hard to get a good score out of it. So you can see that the XGBoost regressor definitely wins here. To silence that, let me try it quickly. It's something like, there it is, objective equals, and it's in quotes. They're just trying to notify you of some change. Okay, it doesn't really matter for us. It just silences the warrant. I thought it did. Oh no, that's the one deprecated in favor of the squared error. Okay. So, excuse me. The squared error in there. You can see it just looks better. You don't want those errors in the output. So do the same thing in the other one as well. Okay, and here by the way, objective, this has to do with how they're computing their errors in their end, how the model works behind the scenes for you. Okay, so there you see how to use Crossfell Score for a lot of different scoring regression, well, a lot of different models using an alternative regression metric, which is my norm. It's the norm of most machine learning contests, and I would say even publications. It's kind of the norm. So the negative mean squared error, you've got to convert it into the root mean squared error. I called it scores, but I could have called it the RMSE. That could be a little more indicative, right? It's the RMSE. So you're printing out the RMSE, the root mean squared error, and the RMSE mean. Your variables can mean something. Think about them when you put them in and the names of your functions. Okay? You keep up the great work.